Thank you very much, Logan. My topic is different with plasmonics. People always compare photonic crystal and the plasmonic sensor for biomolecule detection. Actually, I'm thinking they are not competing technology, they are complementary. For some application like high throughput screening, for high throughput screening, photonic crystal has some advantage, but if you want to look at very limited confined spot, those plasmonic sensor are definitely better than photonic crystal sensor. My topic here is about how to use photonic crystal to enhance fluorescence emission from dye molecules. So the motivation is like we're trying to get more photon out of fluorescence dye. The reason of that is to improve the detection sensitivity. You can imagine if you have very low number of fluorophore, it's very hard to measure them. Using photonic crystal, as shown in this figure, is on photonic crystal surface, which is compared on glass surface. So it's easy to see those molecules. Another advantage is using our substrate by enhance the fluorescence emission. It is possible to increase the measurement speed. It allows you to scan your sample much faster. So it also can help you to reduce the instrument cost. You can think about when you have very low number of photons, you have to use very sensitive detector or use a very expensive CCD camera and powerful lasers. But when you use the enhancement, when you use a substrate with enhancement capability, it will allow you to use low-cost detector and not very expensive lasers. So the application I'm going to show you, including the microarray application and the fluorescence-based genome sequencing. Professor Liu just give you a very thorough introduction about genome sequencing and protein detection. So I hope you must have learned how important those topics are. Actually, our substrate can be used for the fluorophore detection that is immobilized on the sensor surface. So in my talk, I will first show how this structure looks like, how it works, and show the principle why our photonic crystal can be used to enhance fluorescence emission, and spend some time to discuss the different methods that we tested to fabricate those photonic crystal structure, and show you the detection instrument we prototyped in the lab, and talk about two specific applications. One is cancer biomarker detection, another is for the genome sequencing. So the one-dimensional photonic crystal structure is quite simple, which is shown in this figure. It consists of a low refractive index grating substrate, which is coated by high refractive index dielectric layer. So the high refractive index dielectric layer functions like a wave confinement layer. And the incident light, the illumination, will be coupled into this waveguide layer by light diffraction through the grating. So what is the optical response of this structure that is shown in this figure? To be specific, this figure represents the measured reflection spectrum versus incidence angle. So that tells you, for example, you want to couple a laser light which has a wavelength at lambda, you have to illuminate this light at specific angle theta phi. So this structure, we also call it like a photonic band diagram. So this band diagram can be engineered by changing the parameters of the grating structure, including the refractive index of the material and the geometric structure like the grating period, the etching depth, and the thickness of the dielectric coating. How this structure can enhance fluorescence emission? There are two mechanisms. One is enhanced excitation, another is enhanced or directional photon extraction. So let me first look at enhanced laser excitation. So laser that is used to excite fluorophore, which are already immobilized on sensor surface, will be coupled into a resonance mode that is supported by the one-dimensional photonic crystal structure. So this figure shows a simulated near-field distribution within one period of the photonic crystal structure. Since our 1D PC is a periodic structure, in the simulation, we use periodic boundary condition on the left and right side. The scale of this figure, the x-axis is 360 nanometer, and the z-axis is 600 nanometer. So when the light is coupled into resonance, you can see here the black line represents the surface of sensor. So you can tell from the color bar, its color is normalized to the incident light. So the near field gets much stronger, which is 2,500 times stronger than incident light. So in this case, if there is a fluorophore near the sensor surface, fluorophore will feel much stronger field compared to the incidence field. So the emission will be enhanced. So there's two images shows the comparison when the laser light is not coupled into resonance, which is shown in the left figure. And when the incident light is coupled into resonance, you can see those fluorescence emission becomes very, very strong. And those microarrays are made by non-contact printing. The second mechanism of this enhancement is called enhanced extraction. So photons emitted by the fluorophore will be coupled into the photonic crystal resonance mode, and then it will be leaked out of the grating surface while diffraction grating, which is given by this equation. So to take advantage of this enhanced photon emission, it's necessary to have the emission spectrum of the fluorophore overlap with the resonance mode of the photonic crystal structure. So as you see in this figure, so we coat the dye molecule on top of the photonic crystal surface, so, and then measured emission spectrum versus angle, which vary from 0 to 15 degrees. So most of the photons are confined between 0 to 10 degrees, depends on the mode. If you want to look at 620 nanometer, you can only look at a very limited number of angles. Some other method to enhance fluorescence emission, including chemical amplification, which use enzyme molecule with pteramide. So the dye molecule will be amplified. But the advantage of this, the disadvantage of this method is need one actual step to amplify the number of fluorescence molecule, and also it suffers from the diffusion of those dye molecule. So it cannot be used with very high density microarray application. Another method is the metal enhanced fluorescence. So metal enhanced fluorescence has been extensively studied, but this method suffers from the quenching problem, which means if there's a fluorophore get very close to the metal surface, the emission of those dye molecule will be quenched. So people have to precisely control the position of this dye molecule. So if this molecule is too far from the metal surface, there won't be any enhancement. But if this molecule is too close to the metal surface, its emission will be quenched. On contrast, our photonic crystal doesn't have the quenching problem, and also is a dielectric material and is transparent. In some application, you want to illuminate your sample and from one side and the image from the other side, so which you cannot do with a metal substrate. So we have advantage of be able to image and illuminate from different sides of the sample. So when working in a company, before I came back as postdoc in Professor Cunningham's group, so I work as SRO Biosystem, a startup company founded by my advisor. So we test a lot of methods which trying to make those substrate manufacturable, and then we can sell them and make profit. So we test a lot of different methods. So you have been to our lab to to do the rectum molding yourself. So this method is quite simple. I'm not going to go through the detail of this method. This method is good, and that we can make the sensor really cheap on very large scale. So as you see in this figure, is the photonic crystal enhanced fluorescence sensor that same as the size of microscope slice. The one problem for the nano rectum molding method is people have to use plastic material. You have to use plastic substrate which is flexible and also is rely on those UV curve epoxy. Both of them has very high autofluorescence level. So those background, the autofluorescence is a background signal for fluorescence detection. It prevents you from seeing very low concentration of fluorescence molecule. So in order to solve that problem, we use a step-and flash imprint lithography tool. So this method can help people to make any nano structure on rigid substrate. So it's including silicon and quartz. Both of them had very low autofluorescence signal. So 3 years ago, we purchased a molecular imprint machine, which is in the micro nanotechnology clean room. So the first few steps of step flash imprint lithography, same as replica molding. We start from a template and squeeze UV curve polymer between the template and substrate, and then apply the attached template onto the substrate and squeeze those UV curve polymer material. After UV curing, the template will be removed from the substrate. So those steps are similar to the nano replica molding, but after that, since this method is very controllable, it allows us to control the uniformity of this imprint layer. So we will be able to etch back the imprint resist and expose substrate, and then use reactive ion etching to transfer the pattern into substrate. So after we removed the imprint resist, we coat high refractive index dielectric layer to get those photonic crystal structure. So this is how the structure looks like. So our structure has a period of 400 nanometer with grating depth of 40 and duty cycle 50%, which is shown in this AFM image, and also check the cross section of the structure using SEM. So in my hand, that is 1 by 3 inch glass slide, which is almost fully covered by photonic crystal structure. So the optical response of our structure is very sensitive to the angle change when you illuminate the laser onto the sensor substrate. So it's very important to keep a good coupling between the incidence light and the resonance mode of the photonic crystal structure. In order to do so, we prototyped a special detection instrument, so which can provide us more than 90% of coupling between the light of incidence and the resonance mode. And we can also control the angle of incidence to match the resonance point. So it's also required to have high power density to get a good signal-to-noise ratio, and it should be able to scan fast with high spatial resolution near like 1 to 2 micron. So those two figures showed the dispersion relationship of this one-dimensional photonic crystal structure. So the left one is measured when we change the incidence angle along theta direction. We illuminate the substrate with a broadband light and measured transmissions reflection spectrum. So when we change angle along theta direction, since there's no variation along the grating, it's uniform. So this is what we see. This reflection wavelength is independent of angle of incidence. However, if you illuminate along phi direction, which is perpendicular to the grating period will look different when you change the angle. So the result is you will see the band diagram is very sensitive to angle change. So which tell us we want an illumination that doesn't have any angle variation along phi direction, but we can have angle variation along theta direction. So that illumination will look like a line. So we can focus the laser into a line. We still can couple the incidence laser with the resonance mode of photonic crystal pretty well. So this picture shows the equipment we prototyped in the lab. So light from a laser diode is focused by cylindrical lines. Form a line at back focal plane of the objective. So the objective will do Fourier transform will flip the line and still keep the shape of a line and onto the substrate of photonic crystal, onto the surface of photonic crystal. So it's possible to tune the angle of incidence by move the position of this line on the back focal plane of the objective. So this image shows how this line looks like. So the width of the line is 4 micron. So it can cover full field of view of the objective. So when we took a cross section which showed the intensity of line in this figure, you see it's pretty sharp. And we took cross section along the line is kind of uniform with variation less than 15%. And in our software, we normalize this intensity variation. So we calculate the coupling efficiency. So in this configuration, we can achieve 90% of coupling between the light of incidence and the resonance mode. So the angle of incidence can be tuned from 0 to 20 degrees, and the power density we achieve is 3 watt per millimeter square. So how it looks like if you do a real fluorescence measurement. So what we did here is on top of the photonic crystal sensor, we coat a dye-doped polymer layer. So its dye is a Rotmin 700, which can be excited by Heine laser at 633 nanometer, and they emit near 690 nanometer. So when we check the coupling efficiency, which is we measured the transmission versus angle. If transmission is low, that means the coupling is good. So when we approach the resonance angle, the transmission is less than 10%. We got pretty good coupling. So at the same time, if when the light is coupled to the resonance mode, you see very strong signal for the fluorescence. So if you don't couple the incidence light with the resonance mode of photonic crystal substrate, the fluorescence signal is pretty low. So as a proof of concept experiment, we use a simple conjugate polypeptide. So we spot array of this dye-tagged polypeptide at different concentration, 7 different concentration. Each concentration we make nice spot. And measured fluorescence emission image. So as an example, we take cross-section along the fluorescence image and plot the intensity profile in this figure. So as you can see, on the photonic crystal surface, the fluorescence emission intensity is pretty strong. It's much more stronger compared to the fluorescence intensity on glass substrate. So we calculate enhanced factor is around 700 times. Its enhancement is big. However, it's not only enhanced the signal, it's also enhanced background. So in this figure, we plot the signal to noise ratio in terms of concentration. So the signal to noise ratio is defined as signal over the noise of the local background, which is taken near the fluorescence spot. So we plot a circle here to calculate the background intensity, and the standard deviation of that signal is defined as noise. So usually people use signal to noise ratio equal to 3 as the limit of detection, which means if you have signal to noise ratio smaller than 3, that molecule cannot be detected. If it's above 3, so it's easy to be seen. So in this figure, the black curve shows the signal to noise ratio versus concentration that measured on photonic crystal substrate. The red curve means that measured on glass substrate. It's very clear for each concentration, the photonic crystal substrate provide much higher signal to noise ratio. And if you look at the limit of detection, so on glass substrate, you can only see see a very high concentration, which is 6.5 microgram per mil. In compared with that value, the photonic crystal sensor are able to see 45 nanogram per mil, which is 140-fold lower than the concentration that you can see on glass substrate. So for more complicated bio-experiments, we use cancer biomarker microarray as an example. So what is biomarker? They are small molecule or proteins relevant to a certain type of disease. So detection of low concentration of biomarker is very desirable for early disease diagnosis. So for complete disease like cancers, if you only detect one type of biomarker, that is inconclusive. So usually people use high throughput method like microarray method to monitor different type like 100 or thousands of biomarker simultaneously. So like is shown in this figure is taken from a protein biomarker microarray. So different spots represent different biomarker. Like actually when we make this microarray, we spot different antibody at different position. So compared to other cancer diagnosis method, this method has minimal invasive and is very low cost, has advantage of rapid detection. And how the photonic crystal can help for the cancer marker detection? Due to the enhancement phenomena, the photonic crystal can improve the sensitivity of microarray detection. It's also allow detect of low concentration biomarker. It's enabled early cancer screening. So let me show you how we made those cancer biomarker microarray and how this immunofluorescence assay works. So on top of the photonic crystal substrate, which is functionalized with certain type of silane, we first spot different type of antibody. So it's our collaborator give us like 24 different type of antibody, which belongs to 5 different families. So we use a non-contact printing method to print pretty high concentration of antibody, which are at 2 milligram per mil. So we first print antibody, different type of antibody on the substrate, and then block the substrate using a blocker to prevent other type molecule attach on surface. So next step is add the serum. Serum sample contain a mixture of different type of biomarker. So after incubation, the bioaccumulated detection antibody is added on the substrate. And then we use Sci-Fi fluorescence labeled strep evidence as a reporter. So the fluorescence intensity is related with concentration of the biomarker in serum sample. So when we look at the results, the left image shows the fluorescence image from a commercial substrate. So each sub-block contains a panel of 22 biomarkers, and each of those 22 biomarkers will be repeated 8 times. So eventually, the signal intensity will be averaged between different repeats. So the pseudo color represents the intensity of the emission. You can see on photonic crystal substrate, the fluorescence emission intensity is much stronger than the commercial substrate. So the bottom figure summarizes the fluorescence intensity versus different type of biomarker. On average, the enhancement factor is 10 to 30-fold. So how will that help for the linear detection? How will that enable us to see lower concentration of biomarker? So in order to demonstrate that, we plot the dose response curve, which means fluorescence intensity signal versus the concentration of the biomarker. So on our substrate, so each of those blocks contains all the 8 repeats of 22 biomarkers. So we use different concentration of serum, and each of serum is diluted 7 times from 10,000 picogram to 0.6 picogram. So use TNF alpha as an example. This figure shows the dose response curve. Each spot means one concentration. And on the photonic crystal substrate, you can see the intensity of fluorescence is much stronger than that on glass substrate. So we analyze the dose response curve using a software, using a free software from PNL, which called Protein Microarray Analysis Tool, that can help to calculate limit of detection from dose response curve. So among those different assays, we find out the highest improvement is 96%. The improvement was calculated by the difference of the limit detection on photonic crystal substrate and on glass substrate divided by limit detection on glass substrate. So this table tells us the photonic crystal substrate offered benefit of detecting biomarkers at much lower concentration. So people always ask us, can you enhance, can your substrate be used for different type of laser? What I have shown before, they are excited by a red laser at a particular wavelength. But there's a lot of dyes. Some of them need a green laser to be as an excitation source. Some of them need a red laser. So can we use different type of dye with different type of laser? So here we demonstrate enhancement of photonic crystal for both Psi5 and Psi3 dye. The absorption spectrum of Psi5 and Psi3 is shown in this figure. So Psi5 has strong absorption at 633 nanometer, and Psi3, usually people use green laser as an excitation source. So its dispersion relationship tells us how to get enhancement for both dyes. So if you want to excite Psi5 dye, so which the excitation laser is 633 nanometer, so we have to illuminate substrate at 9 degrees to couple light into resonance. On the other hand, if you want to illuminate with Psi3 dye, which is using a green laser, we have to illuminate at 14 degrees. So this diagram shows how we build our instrument. So we have two different lasers. One is helium neon laser at 633 nanometer. Another is Nd:YAG green laser. So we illuminate lasers through a focusing lines. So two lasers has different angle of incidence. So from simulation, you can show the enhancement for both wavelengths. The left figure shows the local field, resonance field distribution, which is coupled with 633 nanometer laser at 9 degrees. So this figure shows the field distribution excited by green laser at 14 degrees. As you can see, both of them has enhancement on sensor surface. So we did a simple experiment to show the simultaneous fluorescence enhancement on the substrate. So the left figure shows the enhancement from Psi5 molecule on photonic crystal. So the black curve is the emission intensity profile taken from this cross section. And if you compare the photonic crystal and glass, our photonic crystal provides 32 times enhancement compared to glass. So simultaneously, you can get enhancement from Psi3 dye, which is a little bit lower because of the difference of the distribution of the resonance mode. I still get like 20 times enhancement from the Psi3 molecule. So the reason that we want to do two-color enhancement is because we were collaborating with a sequencing company, Illumina, trying to help them to improve their sequencing throughput. So Illumina is the leading company in sequencing market. So their chip, which is shown here, is able to measure 30 gig base pair, which contains like 10 times of the size of human genome. So it really takes them 4 days for each sequencing. So in their measurement, the number of photons actually limit the speed of their scan. That's the step that our photonic crystal substrate can help. So in their machine, they use 2 lasers. One is a green laser, another is a deep red laser. And the 2 lasers, one of them excites A and G nucleotide, another excites the other 2 type of nucleotide. So they have 2 lasers and 4 different emission filters. So this figure shows the process of their sequencing. Actually, they start their process with building up the DNA colony. They call it a colony, which represents the polymerase colony. So each step, they will flow different type of dye-labeled nucleotide into the flow channel. So they simultaneously scan 2 lasers and acquire image for different fluorophore. So this is the step our photonic crystal can help. So we collaborate with Illumina. We incorporate our photonic crystal structure into their sample. As you can see in this figure, this block means the region covered by photonic crystal structure. So not the full device is covered by photonic crystal. We leave some blank area as a reference. So our sensor incorporated into their flow channel is scanned using their new, not new, it has been a year, they call it HiSeq 2000 sequencing system. So in their measurement, in their detection machine, they scan a laser beam along the channel direction and measured fluorescence intensity. So this figure shows represent the fluorescence image from a channel. So actually, it's part of the channel. So to see the DNA colony, the poly, we took one spot and zoom in, which is shown in this figure. Each spot represents one DNA colony. So the top part of the channel is covered by photonic crystal. The bottom part of the channel only has glass substrate. You can clearly see on top of photonic crystal, there's the number of photons be collected is much more than that on glass substrate. So it's for this 2 dye A and T, both excited by 60 nanometer laser, it's very clear we have enhancement. So how about the other 2? So the other 2 nucleotides are excited by a green laser, which is it's 532 nanometer. So it show in this figure, we also got enhancement from these 2 types of nucleotide. So the average enhanced factor is summarized in this table. For the red channel, the enhancement is nearly 30 times. For the green channel, is 15 to 18 times. So the results tell us that Illumina can take advantage of photonic crystal to accelerate their fluorescence scan. So as a summary of my talk, I represent the photonic crystal which can provide higher sensitivity and a lower the detection limit, and show you the fabrication method, which is the imprint lithography method that we use to fabricate the photonic crystal on quartz substrate, and talked about the prototype laser line scanner that developed in our lab. And as a proof of concept experiments, we showed the lower limit of detection by 140 times on photonic crystal substrate, and demonstrate the photonic crystal can improve sensitivity of cancer biomarker detection by 6 to 90%, and also give briefly show the photonic crystal can enhance the emission from multiple dye and talk about how that can be used for genome sequencing. So currently, in the lab, we have 3 different directions that we further develop for the photonic crystal sensor. One is called analysis of whole blood. So we collaborate with a group at Harvard to integrate photonic crystal sensor with microfluidic system. We hope we can just make a fluidic system that can separate the serum from the human blood and do the serum quantification that take advantage of PC sensor to get early stage diagnosis of cancer. And the second product we're working on is called photonic crystal enhanced fluorescence cell imaging. So our target is probably you have here my advisor Brian Cunningham talk about label-free cell imaging. We're trying to combine these 2 technology to take advantage of long-term measurement of label-free and specific measurement of fluorescence. So that will be done with using one sensor and on one instrument. The third direction is called PC-enhanced nonlinear optic effect. We are trying to use photonic crystal to enhance the surface-enhanced Raman measurement from those molecule-linked metal nanoparticles. So as for acknowledgement, I thank the member of the non-sensor group who has contributed to this work, and also our collaborator Rick Sanger at Pacific Northwest National Lab, and Nabil at Nano Inc., and Dr. Ren and Dr. Moon at Illumina. Also thank NSF and NIH for their funding and support.
Question? Time for question. One question.
In the sequencing of the genome the cell in your lab, do you have the same type of detector? The CCD is involved, or one is detector?
So actually for the sequencing, we made the device and sent the device to Illumina. They measured for us. So both lasers and I remember they use time-delayed integration camera, TDI CCD camera. So they both incorporate in their machine. So they simultaneously, multiplies the measurement using one CCD camera to measure 4 different channels simultaneously.
Have you tried using a different detector? Do you create the sensitivity?
We haven't tried to measure that ourselves. So it's the goal is to provide the device to Illumina and hope they can license our technology, and they want to use this technology in their tool. So they're probably going to develop some new tool, but it's kind of like collaboration with a big company.
Any other question?
You said at the beginning that it's not really competitive with SIRS sensing, but it does look quite similar, the sort of microarrays, arrays or detection of biomarkers. Can you explain why you think, what are the main differences and that mean they're not competing against each other as technologies, because the SIRS stuff looks like it had high sensitivity?
So you mean compare with plasmonic sensor? So I think for label-free, without using fluorophore, plasmonic sensor and our photonic crystal sensor both have their advantage and disadvantage. But for the fluorescence part, our photonic crystal has advantage of there's no quenching, no fluorescence quenching, so you don't have to control precisely control the position of fluorophore. So it's pretty hard to add those spacers between the substrate and the fluorophore. So that's the advantage of our technique.
What's the maximum distance where you observe, or the repetition of the fluorescence enhancement?
Let's see. I should show here. So as showed in this figure, I think if you get away from surface, the enhancement will become lower. like 100 to 200 nanometer, that is usually what we have. And we also be able to engineer the structure to get the more extension or more confined resonance mode. So that's kind of controllable.
All right, if there's no more question, let's thank Dr. Liu again. And, this is the morning session. I think Marina's coming.